On July 1st, 2025, at precisely 3:47 a.m. Universal Time, a telescope perched high in the Chilean Andes detected something that would challenge everything we thought we understood about visitors from beyond our solar system. The asteroid terrestrial impact last alert system, known by its acronym ATLAS, captured a faint point of light moving against the background stars at a speed that should have been impossible for anything naturally occurring in our cosmic neighborhood. The automated detection algorithms flagged it immediately, not because of its brightness, which was unremarkable, but because of its trajectory. This object was moving wrong. It was traveling in the opposite direction to nearly everything else in our solar system, racing through space at 58 kilometers per second, fast enough to cross the distance from New York to Los Angeles in less than a minute. And it was coming from somewhere we had never sent a probe, never observed directly, never truly understood. It was coming from the space between the stars. Within hours, the discovery was confirmed by telescopes across 3 continents. Within days, it had been designated 3I Atlas, marking it as only the 3rd interstellar object ever detected passing through our solar system. Within weeks, it would become one of the most observed, most analyzed, and most controversial astronomical discoveries of the decade. And within months, it would force scientists, governments, and ordinary people around the world to confront questions that science fiction had been asking for generations, but that hard science had always avoided. Questions about whether we are alone, questions about whether the universe is as empty and indifferent as we have always assumed, questions about what happens when something from out there comes here. The story of 3I Atlas is still unfolding. Right now, as you listen to these words, the object is approaching the most critical moment of its journey through our solar system. On October 30th, it will reach perihelion, the point of closest approach to the Sun, where temperatures will soar, where ice will turn to gas, where stress will mount on every molecule of its structure. It is the moment when comets confess their secrets. It is the moment when objects that have been hiding their true nature can no longer pretend. And it is the moment when, if 3I Atlas is something other than what it appears to be, we might finally have our answer. But before we can understand where this journey leads, we need to understand how we got here. We need to trace the path that brought an object billions of years old and trillions of kilometers traveled into our small corner of the universe. We need to examine the evidence that has accumulated in the months since its discovery, evidence that has both clarified and deepened the mystery. We need to understand what makes 3I Atlas different from every other comet we have ever studied, and why those differences matter. And we need to confront the uncomfortable possibility that has been whispered in academic papers and shouted across internet forums, the possibility that this visitor might not be entirely natural. This is the complete story of 3I Atlas. Everything we know, everything we suspect, and everything we still cannot explain. If you find yourself drawn into this cosmic mystery as much as I have been, go ahead and hit that like button and subscribe to stay updated as this story continues to develop. Tell me in the comments where you are listening from, what time it is there, and what you think this object really is. And if you want to help our community grow, share this investigation on your social platforms. Thank you for always having our back. Now let's begin at the beginning, in the moments before dawn in the Chilean desert, when a machine designed to protect Earth from asteroid impacts stumbled upon something far stranger than anyone had anticipated. The Atlas telescope system was never meant to discover interstellar objects. Its mission is more immediate and more urgent. Every night, when weather permits, the twin Atlas telescopes in Hawaii and Chile scan the sky systematically, searching for asteroids that might pose a threat to Earth. They are part of humanity's planetary defense network, automated sentinels that can detect space rocks weeks or months before they might impact our planet, giving us precious time to calculate trajectories, assess dangers, and potentially mount a defense. The system has been remarkably successful. Since its deployment, Atlas has discovered hundreds of near-Earth asteroids, including several that have passed uncomfortably close to our planet. It works by taking multiple images of the same patch of sky, separated by short intervals, then comparing those images to detect anything that moves. Stars remain stationary between exposures, but asteroids, comets, and other solar system objects shift position, revealing themselves through their motion. On that July morning, the Atlas telescope at Rio Hurtado in Chile was conducting its routine survey of the southern sky. The telescope itself is modest by modern standards, with a mirror just half a meter across, but what it lacks in size it makes up for in coverage. Each exposure captures an enormous field of view, allowing it to survey large swathes of sky quickly and efficiently. The images it captured that night were automatically processed by software designed to flag anything unusual, and at 3:47 a.m. Universal Time, the system registered a hit. Something was moving through the field of view at a velocity that immediately marked it as interesting. The detection was logged, coordinates were recorded, and within hours, other observatories around the world were being notified that something new had been found. What those follow-up observations revealed was extraordinary. This was not an asteroid on an elliptical orbit around the Sun, following the same basic path that countless other rocks have traveled for billions of years. This object was on a hyperbolic trajectory, which meant it was moving too fast to be gravitationally bound to our solar system. It had come from somewhere else it was passing through, and it would eventually leave, continuing its journey through the galaxy on a path that would never bring it back to our Sun. This was an interstellar visitor, only the third ever confirmed, and immediately, observatories across the globe began clamoring for a chance to study it before it disappeared forever into the cosmic darkness from which it had emerged. Before we dive deeper into what those observations revealed, we need to understand why interstellar objects matter so profoundly, and why the discovery of each new visitor from beyond our solar system represents a moment of almost incalculable scientific value. To understand that, we need to step back and consider what we actually know about the universe beyond our immediate cosmic neighborhood. Our solar system is, in cosmic terms, a tiny bubble of order floating in an ocean of emptiness. The Sun and its family of planets, moons, asteroids, and comets occupy a region of space that extends perhaps 1 or 2 light years from our star, depending on how you measure it. Beyond that lies interstellar space, the vast gulf between stars where densities drop to almost nothing and temperatures hover just a few degrees above absolute zero. For all of human history, we have been confined to our bubble, studying only the objects that orbit our Sun, analyzing only the materials that condensed from the disk of gas and dust that gave birth to our planetary system 4.6 billion years ago. We have sent probes to every planet, landed on asteroids and comets, returned samples from the Moon and from near-Earth space. We have learned an extraordinary amount about our own solar system, but until very recently, we knew nothing directly about the materials, the chemistry, the composition of objects that formed around other stars. Interstellar objects change that equation. Each visitor from beyond our solar system is a sample, a piece of another star system that has traveled across the galaxy and conveniently delivered itself to our doorstep for study. These objects formed in environments that may have been radically different from our own, around stars of different masses, different temperatures, different chemical compositions. They condensed from clouds of gas and dust that were enriched by different generations of supernovae, shaped by different gravitational forces, exposed to different radiation environments. Every measurement we make of an interstellar object is a measurement of conditions in another part of the galaxy, a glimpse into the diversity of planetary systems and the range of materials that exist beyond our narrow experience. But interstellar objects are also vanishingly rare, or at least they were thought to be until recently. For all of human history up until 2017, exactly 0 interstellar objects had been definitively detected passing through our solar system. The theoretical models suggested they should exist. After all, we know that planetary systems eject material during their formation. When giant planets migrate inward or outward under the influence of gravitational interactions, they scatter smaller bodies in all directions. Some of those bodies fall into their parent stars. Some settle into stable orbits. And some are flung outward with such velocity that they escape the star's gravitational pull entirely, becoming wanderers in the galaxy, traveling between stars for millions or billions of years until occasionally they pass close enough to another star system to be detected. The models predicted that such objects should pass through our solar system regularly, perhaps a few per year, but they also predicted that those objects would be extremely difficult to detect. They would be small, dark, fast-moving, and visible for only a brief window as they pass through the inner solar system where our telescopes are concentrated. Detecting them would require both luck and sophisticated survey systems capable of scanning large areas of sky repeatedly and identifying objects that moved with unusual velocities. For decades, we lacked those survey systems, and so interstellar objects remained theoretical, predicted but never observed. That changed on October 19, 2017, when the Pan-STARRS telescope in Hawaii detected an object that would soon be designated 1 Oumuamua, meaning scout or messenger in Hawaiian. The discovery of Oumuamua was transformative not just because it confirmed that interstellar objects exist and can be detected, but because of how strange the object turned out to be. Initial observations suggested it was elongated, perhaps 10 times longer than it was wide, shaped like a cigar or a pancake, depending on how you interpreted the light curve data. It showed no signs of cometary activity, no coma of gas and dust, no tail, nothing to suggest it was shedding material as it approached the sun. And yet, as it moved away from the sun, astronomers detected a small, non-gravitational acceleration, a slight deviation from the path that pure gravity would dictate. For normal comets, non-gravitational acceleration is routine. It happens when ice sublimates off the surface, releasing gas that jets away from the nucleus and acts like a tiny rocket engine, giving the comet a push. But Oumuamua showed no visible outgassing, no coma, no tail, nothing that would explain the acceleration in conventional terms. Scientists proposed a variety of explanations, some involving exotic compositions like solid nitrogen ice that would sublimate without producing visible clouds, others suggesting that Oumuamua might be a fragment of a larger body with unusual properties. And one scientist, a Harvard astrophysicist named Avi Loeb, proposed something more radical, that Oumuamua might not be a natural object at all, but a piece of technology, perhaps a light sail designed to be propelled by starlight, sent by an extraterrestrial civilization to explore other star systems. Loeb's hypothesis was controversial, to put it mildly. Most scientists argued that the evidence did not warrant such an extraordinary conclusion, that natural explanations, however exotic, were always preferable to invoking alien technology. But the debate over Oumuamua established a precedent, a framework for thinking about how we might recognize artificial objects in space and what criteria we should use to distinguish them from natural ones. That framework would become critically important just 2 years later when the second interstellar object was discovered. On August 30, 2019, amateur astronomer Gennady Borisov, using a telescope he had built himself at the Margot Observatory in Crimea, detected a comet that would be designated 2I Borisov. Unlike Oumuamua, Borisov behaved exactly like a comet should. It had a clear coma and tail, it released gas and dust as it approached the sun, its composition appeared similar to comets from our own solar system. Spectroscopic observations revealed water vapor, carbon monoxide, and other molecules familiar from solar system comets. Borisov was interesting because it was interstellar, providing our first opportunity to study the composition of a comet formed around another star. But it was not mysterious. It did not challenge our understanding or force us to consider exotic explanations. It was simply a comet from somewhere else, behaving exactly as comets do. And then came 3I Atlas. When the Atlas telescope detected the third interstellar visitor on July 1, 2025, astronomers immediately began the process of characterizing its properties. Was it more like Oumuamua, inactive and enigmatic? Or more like Borisov, a straightforward comet that just happened to come from interstellar space? The answer, it turned out, was neither. 3I Atlas would prove to be something entirely its own, exhibiting a combination of properties that had never been seen before in any object, interstellar or otherwise. And as the observations accumulated, as telescopes around the world and in space turned their attention to this visitor, the list of anomalies grew longer and more difficult to explain using conventional cometry physics. Let's start with the most basic question. What is 3I Atlas and where did it come from? The designation tells us part of the story. The 3I marks it as the third confirmed interstellar object, following Oumuamua and Borisov. The Atlas refers to the survey telescope that discovered it, but those labels tell us only about its relationship to Earth and to our detection systems. They tell us nothing about what the object actually is or where it originated. To understand that, we need to trace its trajectory backward through space and time. Every object in the universe moves under the influence of gravity, following paths determined by the masses and positions of nearby bodies. By measuring an object's position and velocity with sufficient precision, we can calculate its orbit, both where it is going and where it has been. For 3I Atlas, those calculations reveal a hyperbolic trajectory, meaning the object is moving faster than the sun's escape velocity at its current distance. It is not bound to our solar system. It entered from interstellar space, it is passing through the inner solar system, and it will exit back into interstellar space, traveling onward through the galaxy until perhaps billions of years from now. It passes close enough to another star to be perturbed by that star's gravity. But where did it come from originally? This is a much more difficult question to answer because the object has been traveling for a very long time. Current estimates suggest that 3I Atlas may be anywhere from 3 billion to 11 billion years old. Think about what that means. If the object is 11 billion years old, it formed when the universe itself was only about 2.7 billion years old, less than 20% of its current age. It would have condensed from a cloud of gas and dust, enriched by the very first generations of stars, when the chemical composition of the galaxy was radically different from what it is today. It could have witnessed the formation of our own solar system 4.6 billion years ago, passing somewhere in the distance as the sun ignited and the planets began to coalesce. It has been wandering the galaxy for longer than complex life has existed on Earth, longer than our planet has had continents or oceans or an oxygen-rich atmosphere. Tracing the object's path backward through space is complicated by the fact that it has been influenced by the gravity of every star and molecular cloud it has passed near during its journey. Those gravitational perturbations alter its trajectory slightly, and over billions of years those small changes accumulate, making it nearly impossible to determine precisely which star system ejected it originally. What we can say is that 3I Atlas entered our solar system from the direction of Sagittarius, from the general direction of the galactic center. That region of sky contains hundreds of billions of stars, and without more precise information about the object's trajectory and velocity before it encountered the sun's gravitational influence, we cannot narrow down its origin further. But we can learn about its history in other ways, through its composition, its structure, its behavior, as it responds to the sun's heat and light. And this is where 3i Atlas begins to reveal its secrets and its mysteries. When an object from interstellar space enters our solar system, it begins to warm. In the cold darkness between stars, temperatures hover around 3 Kelvin, just 3 degrees above absolute zero. At those temperatures, everything is frozen solid. Water ice is as hard as steel. Carbon dioxide, methane, nitrogen, even molecular hydrogen can exist as ices, coating the surfaces of interstellar objects and preserving them in a state essentially unchanged since they first formed. But as an object approaches a star, it begins to absorb radiation. The surface temperature rises, and at certain critical thresholds, different ices begin to sublimate, transforming directly from solid to gas without passing through a liquid phase. For 3i Atlas, that warming process began long before it entered the inner solar system. In fact, one of the most surprising early discoveries about this object was that it appeared to be active when it was still extraordinarily far from the Sun. Most comets in our solar system begin showing signs of activity, developing a coma of gas and dust around their nucleus when they reach about 3 astronomical units from the Sun. An astronomical unit is the distance from Earth to the Sun, about 150 million kilometers, so 3 AU is roughly 3 times that distance, around where the asteroid belt is located between Mars and Jupiter. But 3i Atlas was showing signs of activity much earlier, when it was still 6 astronomical units from the Sun, out near the orbit of Jupiter. This early activity suggests that the object contains highly volatile materials, substances that sublimate at very low temperatures. Nitrogen ice begins to sublimate when sunlight warms it to around 35 Kelvin. Carbon monoxide ice sublimates at temperatures above 20 Kelvin. These are temperatures that can be reached far from the Sun, and the fact that 3i Atlas was active so early suggests its surface or near-surface layers contain these exotic ices. This is unusual but not unprecedented. Some comets from the Oort cloud, the distant spherical shell of icy bodies that surrounds our solar system, contain significant amounts of nitrogen and carbon monoxide. But it does tell us something about where and how 3i Atlas formed. It suggests that the object condensed in a region of its parent star system that was cold enough for these volatile materials to freeze out, which likely means it formed in the outer regions of a planetary system, perhaps analogous to our Kuiper belt or Oort cloud. As 3i Atlas continued its inward journey, approaching the Sun and warming further, observatories around the world tracked its progress, measuring its brightness, monitoring its activity, taking spectra to determine what gases it was releasing. And this is where the real surprises began to emerge. The first major observatory to capture detailed observations of 3i Atlas was NASA's Hubble Space Telescope. Getting time on Hubble is notoriously difficult. The telescope is one of the most oversubscribed scientific facilities in the world, with far more proposals for observations than time available. Astronomers must submit detailed requests months in advance, arguing their case in competition with hundreds of other research teams. But Hubble reserves a small amount of time each year for so-called targets of opportunity, objects that appear unexpectedly and need to be observed quickly before they disappear. Interstellar visitors certainly qualify as targets of opportunity, and so 3i Atlas jumped to the front of the queue. On July 21, 2025, when 3i Atlas was 446 million kilometers from Earth, Hubble's Wide Field Camera 3 captured a series of images that provided our first clear look at the comet's structure. The images are striking. You can see the central bright nucleus surrounded by a diffuse coma of gas and dust. The stars in the background are stretched into streaks because the telescope was tracking the comet as it moved. compensating for its motion to keep it centered in the field of view while everything else appears to trail past. The comet itself shows a teardrop shape, with material streaming away from the nucleus in the direction opposite the Sun, exactly what you would expect from a comet being pushed by solar radiation pressure and the solar wind. But the Hubble observations also allowed scientists to make the first reliable estimate of the nucleus size. Early estimates based on the object's brightness had suggested a diameter of around 10 to 20 kilometers, which would have made 3I Atlas extraordinarily large for an interstellar object, far larger than either Oumuamua or Borisov. But those early estimates were based on the assumption that all the light we were seeing was reflected sunlight from the nucleus itself. The Hubble images revealed that most of the brightness was actually coming from the coma, the cloud of dust surrounding the nucleus, not from the nucleus itself. When scientists separated the contribution of the coma from the contribution of the nucleus, they arrived at a much smaller size estimate. The nucleus of 3I Atlas is somewhere between 440 meters and 5.6 kilometers in diameter. That range is still quite large, reflecting the uncertainty inherent in this kind of measurement, but it places 3I Atlas much more in line with what we would expect for an interstellar object. It is comparable in size to Borisov and larger than Oumuamua, but not so large as to strain our understanding of how many such objects should exist in interstellar space. Still, even at the smaller end of the size range, 3I Atlas is a substantial body, large enough to have interesting internal structure, large enough to potentially survive its passage around the Sun intact, large enough to warrant the intense scrutiny it has received. The Hubble observations were just the beginning. Within weeks, one of the most powerful observatories ever built would turn its attention to this interstellar visitor, and what it saw would deepen the mystery considerably. The James Webb Space Telescope, humanity's premier space-based observatory for infrared astronomy, represents a technological achievement almost without parallel. With a mirror 6.5 meters across, composed of 18 hexagonal segments coated in gold, operating at temperatures just above absolute zero to minimize thermal interference, Webb can detect the faint infrared light from the most distant galaxies in the universe, can peer through dust clouds to see star formation in action, can analyze the atmospheres of exoplanets orbiting distant stars. It is, in every sense, a telescope designed to observe things that have never been seen before. And in early August 2025, it pointed that extraordinary capability at 3I Atlas. On August 6th, Webb's near-infrared spectrograph, NER-SPEC, captured the spectrum of the comet, spreading out the light into its component wavelengths and revealing which molecules were present in the coma. What that spectrum showed surprised the astronomers analyzing it. Most comets are dominated by water ice. When they approach the Sun and begin to warm, water sublimates off the surface, and water vapor becomes the dominant component of the coma. You typically see a ratio of water to other volatiles like carbon dioxide or carbon monoxide of perhaps 10 to 1 or higher, meaning that for every molecule of CO2 or CO, there are 10 molecules of water. But 3I Atlas showed the opposite pattern. The spectrum revealed strong emission from carbon dioxide and carbon monoxide, but relatively weak emission from water. When the astronomers calculated the ratios, they found that carbon dioxide was 8 times more abundant than water in the coma. 8 to 1, the complete inverse of what we normally see. This is extraordinary and difficult to explain. In our solar system, comets form from the materials available in the protoplanetary disk that surrounded the young Sun. That disk was rich in water ice because oxygen is an abundant element and readily combines with hydrogen, the most common element in the universe, to form water. Carbon dioxide and carbon monoxide are present, but in much smaller quantities. The fact that 3I Atlas has such a carbon dioxide-rich composition suggests it formed in a very different environment, perhaps around a star with a different chemical makeup, or in a region of its parent protoplanetary disk, where the temperatures and pressures favored the incorporation of carbon dioxide over water. There are scenarios that can produce this kind of composition naturally if the comet formed very far from its parent star, in a region where temperatures were low enough for carbon dioxide to condense, but where water had already been depleted through some process. You might get a carbon dioxide-rich body. Or if the comet formed around a star that had a higher carbon to oxygen ratio than our Sun, the disk chemistry could favor carbon dioxide formation. But both scenarios require special conditions, and the fact that Atlas exhibits this unusual composition makes it a valuable probe of the diversity of planetary system environments. The Webb observations also revealed something about the structure of the comet's coma. Instead of being uniform and symmetric, the coma showed complex morphology with different regions showing different levels of activity. This suggests that the nucleus is not uniformly active, that gas and dust are being released preferentially from certain areas, while other areas remain relatively quiet. This kind of regional variation is common in solar system comets, and usually reflects differences in composition or structure across the nucleus surface. Some areas might be covered by a layer of dark, non-volatile dust that insulates the ice beneath, while other areas might have fresh ice exposed that sublimates readily when sunlight hits it. But there was another surprise in the Webb data. The researchers found that a surprising amount of dust was being ejected in the sunward direction, toward the sun rather than away from it. This is counterintuitive because radiation pressure from sunlight should push dust away from the sun. But what the Webb team proposed is that large dust grains are being ejected from the nucleus with significant velocity, perhaps propelled by gas pressure as carbon dioxide sublimates rapidly beneath the surface. These grains travel sunward initially because of their momentum, but as they move away from the nucleus, they begin to fragment, breaking into smaller pieces. These smaller fragments then scatter light more efficiently, which is why we see an enhanced brightness in the sunward direction. It is a dynamic, complex process, and one that speaks to the violence of sublimation occurring on the nucleus as it heats up. But the major space telescopes were not the only observatories paying attention to 3i Atlas. Ground-based facilities around the world, telescopes in Chile, Hawaii, the Canary Islands, Bulgaria, and elsewhere, were also collecting data, and their observations would add yet more pieces to the puzzle. One of the interesting things about science is that sometimes the most important discoveries come from data that was never intended to capture the object in question. This is what happened with the Transiting Exoplanet Survey Satellite, or TESS. TESS is a space telescope designed to find exoplanets by monitoring stars for the tiny dips in brightness that occur when a planet passes in front of its star as seen from Earth. It uses 4 wide-field cameras to survey large swaths of sky continuously for weeks at a time, building up long-time series of observations that can reveal periodic transits. The mission has been extraordinarily successful, discovering thousands of exoplanet candidates since its launch in 2018. But TESS does not only see exoplanets. Its cameras also capture asteroids, comets, and other solar system objects that happen to pass through its field of view. And as it turns out, TESS observed 3i Atlas weeks before the Atlas telescope officially discovered it. From May 7th through June 2nd, 2025, the comet was in a region of sky that TESS was monitoring, and when astronomers went back through the TESS data after the discovery was announced, they found the comet in dozens of individual frames. By stacking those frames together, they could create composite images that showed 3i Atlas much earlier in its approach, when it was still farther from the Sun and less active. What those TESS observations revealed was surprising. Between early May and early June, 3i Atlas got much brighter, far brighter than the distance change alone could explain. Based purely on the geometry, as the comet moved closer to the Sun and to TESS, the scientists expected it to brighten by a factor of about 1.5. Instead, it brightened by a factor of 5. That is more than 3 times brighter than expected, and it indicates that the comet underwent a surge in activity during this period, releasing more gas and dust, developing a larger and brighter coma. This kind of outburst behavior is not uncommon in comets. Sometimes a pocket of volatile material beneath the surface is suddenly exposed, perhaps because an overlying layer of dust is blown away or because a crack opens in the crust. And when that happens, you can get a rapid increase in activity as fresh ice is exposed to sunlight. But what makes the TESS observations particularly interesting is that they show this outburst occurred when the comet was still very far from the Sun, around 4 to 5 astronomical units, much farther out than where most solar system comets begin showing significant activity. This reinforces the interpretation that 3I Atlas contains highly volatile materials that sublimate at low temperatures, and it suggests that the comet has been active for a long time, possibly for the entire duration of its journey through our solar system. The TESS data also allowed astronomers to search for periodic variations in the comet's brightness that might reveal how fast it is rotating. When an elongated or irregularly shaped nucleus rotates, the amount of surface area we see changes periodically, causing the reflected light to vary. By measuring those variations, you can determine the rotation period, which in turn tells you something about the object's shape and structure. The TESS analysis found some hints of periodicity, with signals appearing at around 16 hours and 29 hours, but the data was noisy and the signals were not strong enough to be conclusive. However, other observations using specialized ground-based telescopes have supported a rotation period of around 16 hours, so we can be reasonably confident that this is how fast the nucleus is spinning. A 16-hour rotation period is actually fairly slow for a comet nucleus. Some small asteroids and cometary nuclei rotate much faster, completing a full rotation in just a few hours. The relatively slow rotation of 3I Atlas suggests that it is either fairly large, so that centrifugal forces at the equator are not strong enough to overcome the object's gravity and cause it to break apart, or that it has some structural strength, perhaps because it is not just a loose rubble pile, but contains some cohesion between its constituent parts. This is important because it affects the comet's ability to survive the stresses of perihelion, the point of closest approach to the Sun, where heating and tidal forces are at their maximum. As summer turned to fall and 3I Atlas continued its inward journey, more observations accumulated from telescopes around the world. The Gemini Observatory, with its twin 8-meter telescopes in Hawaii and Chile, captured multi-wavelength images that showed the comet's coma and the beginning of a tail. The Gemini South Telescope in Chile used its multi-object spectrograph to measure the spectrum of the comet in visible light, and these observations confirmed the presence of cyanide molecules in the coma. Cyanide. The word immediately conjures images of poison, of Cold War spy dramas and murder mysteries. But in the context of comets, cyanide is actually quite common and not at all sinister. What astronomers detected was not cyanide in its molecular form, but rather the CN radical, a fragment consisting of one carbon atom bonded to one nitrogen atom. This radical forms when more complex molecules containing carbon and nitrogen are broken apart by solar ultraviolet radiation. In the case of comets, the parent molecule is usually hydrogen cyanide, HCN, which is present in the ice and sublimates as the comet heats up. The ultraviolet light from the Sun then breaks the HCN molecule apart, releasing the CN radical, which fluoresces in visible light and can be detected with telescopes. The detection of CN is significant because it tells us about the nitrogen content of the comet and about the parent molecules present in the ice. For 3I Atlas, the amount of CN detected was actually on the lower end of the range seen in solar system comets, but it was still present, and it was increasing as the comet got closer to the Sun and sublimation rates increased. By early September, the comet was releasing approximately 8 times 10 to the 23rd power CN molecules per second. That is 800 sextillion molecules per second, an almost incomprehensible number, but remember that molecules are extraordinarily tiny. So even releasing that many molecules per second does not represent a huge mass loss from the comet's perspective. But the CN detection led to another interesting finding. By comparing the amount of CN to the amount of another carbon-based molecule, C2 or dicarbon, astronomers can classify comets into different compositional types. Comets with a high ratio of C2 to CN are called carbon chain rich, while comets with a low ratio are called carbon chain depleted. This classification is thought to reflect differences in the formation environments of comets, with different temperatures, pressures, and chemical compositions leading to different ratios of these molecules being incorporated into the ice. When researchers measured the C2 and CN content of 3I Atlas, they found that it was extremely carbon chain depleted, with one of the lowest C2 to CN ratios ever measured for any comet. In fact, upper limits on the C2 production suggested that the comet produces less than 0.09 C2 molecules for every CN molecule it releases. This places 3I Atlas in a distinct compositional class, and interestingly, the previous interstellar comet Borisov also showed carbon chain depletion. Whether this represents a pattern suggesting that interstellar comets in general are carbon chain depleted, or whether it is just a coincidence based on a small sample size, remains to be seen. But it is another data point indicating that 3I Atlas formed in an environment chemically distinct from the inner regions of our solar system, where most of the comets we study originated. As August turned into September, another type of observation was being made, one that would reveal a property of 3I Atlas unlike anything seen before in any solar system object. This observation used a technique called polarimetry, which measures how light is polarized as it scatters off dust grains and gas molecules in the comet's coma. Polarimetry is a powerful tool for probing the physical properties of dust, properties like grain size, shape, and composition that are difficult to measure in other ways. When unpolarized sunlight hits a dust grain, the light that scatters off at certain angles becomes partially polarized, meaning the light waves oscillate preferentially in certain directions rather than randomly in all directions. The degree and direction of polarization depend on the properties of the dust grain and on the geometry of the observation. By measuring polarization as a function of phase angle, the angle between the Sun, the comet, and the observer, you can infer information about what the dust grains are made of and how they are structured. For most comets and asteroids, polarization follows a predictable pattern. At small phase angles, when you are looking at the object nearly head-on with the Sun behind you, the polarization is slightly negative, meaning the light is polarized parallel to the scattering plane rather than perpendicular to it. As the phase angle increases, the polarization transitions to positive and increases. The point where polarization crosses from negative to positive is called the inversion angle, and the depth of the negative polarization branch at small phase angles provides information about the surface properties. When researchers measured the polarization of 3I Atlas using telescopes in Chile, the Canary Islands, and Bulgaria, they found something extraordinary. The comet showed an exceptionally deep and narrow negative polarization branch, deeper and narrower than any comet or asteroid in our solar system. The polarization reached 2.77% at a phase angle of around 7 degrees, and the inversion angle was only about 17 degrees. This combination had never been seen before. For context, most comets show negative polarization depths of around 1 to 2%, and inversion angles between 20 and 25 degrees. 3I Atlas was polarizing light in a way that fell completely outside the known parameter space. What does this mean physically? The polarization properties are determined by the dust grains in the coma, their size distribution, their shape, their composition, and their internal structure. The deep negative polarization suggests that the dust grains are scattering light in a very specific way, different from the dust in solar system comets. One possibility is that the grains have a different size distribution, perhaps with more large grains relative to small ones than we typically see. Another possibility is that the grains have unusual optical properties, perhaps because they are made of different materials or have different internal structures, maybe more porous. The researchers noted that the polarization properties of 3I Atlas were somewhat similar to those of trans-Neptunian objects and centaurs, bodies that orbit in the outer reaches of our solar system and have spent most of their lives in deep freeze, never approaching close enough to the Sun to be significantly altered by solar heating. This comparison suggests that 3I Atlas might be composed of very pristine material, ices and dust that have been preserved in their original state since the object formed billions of years ago. If true, this makes the comet an even more valuable scientific target because it provides a window into the conditions that existed in the outer regions of its parent planetary system when that system was young. But the polarization measurements also raised questions that remain unanswered. Why is 3I Atlas so different from every other object we have studied? Is it truly unique, or does it represent a class of objects that we simply have not had the opportunity to observe before? And what does this tell us about the diversity of materials and formation processes in planetary systems throughout the galaxy? These questions will require more observations, more data, and more theoretical work to answer. But they underscore just how much we still have to learn from this visitor. As September progressed and 3I Atlas moved closer to the Sun, amateur astronomers around the world were also contributing to the observational campaign. One of the most exciting aspects of modern astronomy is that you do not need access to a multi-million-dollar telescope to make meaningful observations. With modest equipment, patience, and skill, amateur astronomers have made significant contributions to comet science, discovering new comets, monitoring the activity of known comets, and capturing images that complement professional observations. On the night of September the 7th through 8th, parts of the world were treated to a spectacular lunar eclipse, a so-called blood moon where the moon passes through Earth's shadow and takes on a reddish hue from sunlight refracted through our atmosphere. For amateur astronomers, a lunar eclipse is a gift. The moon's bright light normally washes out faint objects in the sky, making it difficult to observe comets, asteroids, or deep sky objects. But during an eclipse, the moon dims dramatically, and the sky becomes almost as dark as it would be during a new moon, providing a rare opportunity to observe faint objects that would normally be invisible. Two experienced astrophotographers, Michael Yeager and Gerald Riemann, were taking advantage of this opportunity in Namibia, using their telescopes to capture images of the night sky. And there, in their images, they found 3I Atlas. But something had changed. The comet was no longer the reddish or neutral color it had appeared in earlier observations. It was green, a distinct emerald-tinged hue that extended through the coma, creating a beautiful contrast against the black background of space. For many comets in our solar system, turning green is not unusual. The color comes from a molecule called diatomic carbon, C2, which consists of two carbon atoms bonded together. When solar ultraviolet light excites C2 molecules, they fluoresce at a wavelength around 518 nanometers, which appears green to human eyes. As comets approach the Sun and sublimation increases, more complex organic molecules in the ice are broken apart, releasing C2 into the coma, and the comet takes on a greenish glow. It is a beautiful phenomenon, and one that has been photographed in countless comets over the years. But here is where things get interesting with 3I Atlas. Remember that spectroscopic observations had shown the comet to be extremely carbon chain depleted, with very little C2 production. The upper limits on C2 emission suggested that for every CN molecule the comet released, it produced less than 0.09 C2 molecules. That is far too little to produce a visible green color. And yet here were photographs clearly showing a green comet. How could this be? There are several possible explanations. One is that C2 production had increased dramatically in the days or weeks since the spectroscopic observations were made, and the comet was now releasing much more C2 than before. This would not be unprecedented. Comet activity can vary substantially over time, especially as fresh ice is exposed or as the comet undergoes outbursts. As 3I Atlas got closer to the Sun and heating intensified, it is entirely plausible that C2 production ramped up significantly. Another possibility is that the green color is not entirely due to C2, but includes contributions from other molecules or processes. CN, for instance, can emit in the blue-green part of the spectrum under certain conditions. If the CN emission was strong enough, and the imaging filters or processing brought out the green channel, you might see a greenish hue even without significant C2. Additionally, the images taken by Jaeger and Raman were long exposures designed to bring out faint details, and the color processing used to create the final images can affect how colors appear. It is possible that what looks distinctly green in the processed images is less pronounced in the raw data, but there is also a third, more intriguing possibility. What if the green color is caused by C2, but represents something unusual about how 3I Atlas produces and releases carbon-bearing molecules? What if the comet's composition or structure leads to processes that generate C2 in ways we do not typically see in solar system comets? This is speculative, but it points to the fact that 3I Atlas continues to surprise us, continues to exhibit properties that do not quite fit the standard models. The green comet photographs went viral on social media and astronomy forums. For many people, they represented the first visual confirmation that 3I Atlas was real, was out there, was something you could actually see and photograph. The images captured the public imagination in a way that spectroscopic data and orbital calculations cannot. They made the comet tangible, beautiful, accessible, and they reminded us that the universe is not just a collection of numbers and equations, but a realm of physical objects moving through space, glowing with their own light, telling their own stories. As September drew to a close, 3I Atlas was approaching a critical threshold. It was now less than 2 astronomical units from the Sun, close enough that solar heating was becoming intense, close enough that sublimation rates were accelerating, close enough that stresses on the nuclear structure were mounting, and it was about to disappear from view for several crucial weeks as it moved into the region of sky too close to the Sun for safe observation from Earth. But before it vanished, there was one more major observation campaign, one that would bring the full power of Earth-based astronomy to bear on this visitor and would provide the most detailed measurements yet of its properties. The Very Large Telescope in Chile, one of the most powerful ground-based observatories in the world, turned its instruments toward 3I Atlas in late September, and what those instruments detected would add yet another layer to the mystery. The Very Large Telescope, or VLT, is not actually a single telescope, but an array of 4 massive instruments, each with a primary mirror, 2 meters in diameter. When used individually, each telescope is powerful enough to detect objects billions of light-years away. When used together through a technique called interferometry, they can achieve angular resolution equivalent to a telescope over 100 meters across. The VLT also hosts a suite of specialized instruments designed to analyze light in different ways, breaking it into spectra, measuring polarization, capturing images in multiple wavelengths simultaneously. It is, in short, one of the premier facilities for detailed astronomical observation anywhere on the planet. The instrument used to observe 3I Atlas was UVES, the ultraviolet and visual Echelle spectrograph, which is specifically designed to capture high-resolution spectra in the ultraviolet and visible parts of the spectrum. This is the perfect tool for detecting faint emission lines from metals and molecules in a comet's coma. And when the UVES team analyzed their data, they found something that should not have been possible. They detected nickel. Not nickel compounds, not nickel-bearing minerals, but free nickel atoms floating in the coma, fluorescing as they absorbed ultraviolet light from the sun, and not just a trace amount. The production rate was significant and increasing rapidly as the comet approached the sun. Between late July and late August, covering a period when the comet moved from about 3.9 AU to 3.1 AU from the sun, the nickel production rate increased by a factor of 25. 25 times more nickel was being released per second in late August than had been released in late July. Let me emphasize why this is extraordinary. Nickel is a heavy metal. Its melting point is around 1450 degrees Celsius, and in typical comet nuclei, nickel atoms are locked up in silicate minerals or metal grains embedded in the ice. To release free nickel atoms into the gas phase, you need to either vaporize the silicates, which requires temperatures well over 1000 Kelvin, or you need some chemical process that can extract nickel from solid phases at much lower temperatures. At 3 AU from the sun, surface temperatures on a comet nucleus are only around 200 Kelvin, far too cold to vaporize silicates. So how is 3I Atlas releasing nickel? The researchers who made this discovery proposed one possible mechanism: the formation of nickel carbonyl, a volatile compound that can form when nickel reacts with carbon monoxide at relatively low temperatures. Nickel carbonyl, NiCO4, is actually used in industrial processes on Earth to purify nickel ore. It is a gas at room temperature and decomposes at higher temperatures to deposit pure nickel. If nickel carbonyl is forming in or on the comet nucleus and then sublimating as the nucleus warms, it could release free nickel atoms into the coma when the carbonyl molecules are broken apart by solar ultraviolet light. But there is a problem with this explanation. Nickel carbonyl formation requires not just nickel and carbon monoxide, but specific chemical conditions that are not typical in comets. And there is another issue: where is the iron? In nature, nickel and iron are nearly inseparable. They form together in the cores of dying massive stars, are expelled together in supernova explosions, condensed together in planetary systems. Every meteorite, every asteroid, every sample of cosmic material we have ever analyzed shows nickel and iron together in relatively fixed ratios. When you see nickel, you expect to see iron in roughly 10 times the abundance. But the VLT observations of 3I Atlas detected nickel without corresponding iron, at least in the early observations. Iron emission lines eventually appeared when the comet got closer than about 2.6 AU, but even then, the nickel to iron ratio was far higher than anything seen in solar system comets or in the previous interstellar comet, Borisov. This is deeply puzzling. There are scenarios you can construct to explain it. Perhaps the nucleus contains nickel-rich minerals in some regions and iron-rich minerals in others, and the nickel-rich regions are being preferentially heated or exposed. Perhaps there are chemical pathways involving organic compounds or sulfur that can mobilize nickel more efficiently than iron at low temperatures. But all these scenarios require special pleading, require invoking conditions or processes that are not typical of comets as we understand them. And there is one other explanation that some have suggested, one that involves no comet chemistry at all. What if the nickel signature is not coming from natural sublimation of ice and rock, but from something else? What if 3I Atlas is, or contains, something manufactured? Nickel is extensively used in spacecraft construction. Nickel alloys are valued for their strength, corrosion resistance, and stability across wide temperature ranges. Fuel tanks are often nickel-plated. Structural components use nickel-steel alloys. If 3I Atlas had a metallic surface or structure, solar heating could cause surface materials to vaporize or ablate, releasing nickel atoms that would be detected exactly as the VLT observed. This is not a mainstream interpretation. Most scientists working on 3I Atlas favor natural explanations involving exotic but plausible chemistry. But the nickel anomaly has given ammunition to those who argue that we should not dismiss the possibility of artificial origin without thorough investigation. And that brings us to the most controversial figure in the 3I Atlas story, a scientist who has become both famous and infamous for his willingness to consider explanations that his colleagues regard as premature at best and reckless at worst. Avi Loeb is a name that provokes strong reactions in the astronomical community. By any measure, he is a distinguished scientist. He is the Frank B. Baird Jr. Professor of Science at Harvard University, former chair of the Harvard Astronomy Department, founding director of Harvard's Black Hole Initiative, with over 800 peer-reviewed publications and numerous awards and honors. He has made significant contributions to astrophysics, cosmology, and the study of the early universe. But in recent years, Loeb has become better known to the public for his controversial stance on interstellar objects and the search for extraterrestrial intelligence. It began with Oumuamua. When that first interstellar visitor displayed its unusual properties, the elongated shape, the lack of visible cometary activity, the non-gravitational acceleration, Loeb co-authored a paper suggesting that one possible explanation was that Oumuamua was not a natural object, but a light sail, a thin structure designed to be pushed by starlight, perhaps sent by an extraterrestrial civilization to explore other star systems. The paper was carefully worded, presenting this as one hypothesis among several, but the media seized on it. And Loeb became the public face of the idea that we might have witnessed our first encounter with alien technology. Most of Loeb's colleagues were skeptical, arguing that the evidence did not warrant such an extraordinary conclusion, that natural explanations, however exotic, were preferable to invoking aliens. The debate became heated at times, with some scientists accusing Loeb of damaging the credibility of serious SETI research by promoting speculation without sufficient evidence. Loeb, for his part, argued that scientists should be open to all possibilities and that dismissing the artificial hypothesis out of hand was itself unscientific. When 3I Atlas was discovered in July 2025, Loeb immediately turned his attention to this new interstellar visitor. Within days of the discovery announcement, he had published a preprint paper discussing the object's properties and raising questions about its size and mass. At first, his commentary seemed purely scientific, focused on the mathematics of orbital dynamics and the statistics of how often we should expect to encounter interstellar objects of various sizes. But then, a few days later, Loeb and two collaborators published a second paper with a provocative title. Is the interstellar object 3I Atlas alien? The paper did not claim that 3I Atlas was definitely artificial. Rather, it explored the question as what the authors called a pedagogical exercise, an analysis designed to show how one might approach the problem of distinguishing natural objects from technological ones. They discussed the comet's trajectory, noting that its orbit was aligned within about 5 degrees of the ecliptic plane the flat disk in which the planets orbit. They calculated the probability of such an alignment occurring by chance for a randomly arriving interstellar object and found it to be quite low, around 0.2% or 1 in 500. They noted that the comet's trajectory would bring it relatively close to Venus, Mars, and Jupiter, providing opportunities to observe all three planets, and calculated the probability of this alignment as well, finding it to be even lower, around 0.05%. Loeb and his colleagues also discussed the possibility that 3I Atlas could use a gravitational slingshot maneuver around the Sun to change its trajectory, potentially targeting Earth or remaining in the solar system rather than continuing into interstellar space. They calculated the velocity changes that would be required and the timing that would be necessary, showing that such a maneuver was physically possible if the object had propulsion capabilities. But here is where Loeb's analysis ran into criticism from other scientists. Much of his argument was based on early estimates of the comet's size that placed its diameter at around 10 kilometers, making it extraordinarily massive for an interstellar object. Loeb argued that an object this large entering our solar system should be extremely rare, and that its appearance so soon after Oumuamua and Borisov suggested that either our models of interstellar object populations were badly wrong, or 3I Atlas was unusual in ways that might indicate artificial origin. But by the time Loeb's paper was published, new observations from Hubble had already revised the size estimate downward significantly, showing that the nucleus was probably between 0.5 and 5.6 kilometers across, not 10 kilometers. This made the object less of a statistical anomaly, more in line with what models predicted. Loeb acknowledged the Hubble observations in a blog post, but continued to use the larger size estimates in his analysis, arguing that the uncertainty range still included masses that would be statistically improbable. This struck many scientists as cherry-picking data, using the numbers that supported his argument while downplaying observations that undermined it. Other researchers pointed out that Loeb's trajectory analysis was based on outdated orbital elements, and that when you used the most recent and accurate trajectory data, the claimed alignments with planets were less impressive than he made them sound. In two rebuttal papers, a geoscientist named AKM Easnul Hakwe systematically addressed Loeb's claims, showing that the trajectory of 3I Atlas could be fully explained by natural gravitational dynamics without invoking any propulsion or guidance. Hack noted that Loeb's calculations of non-gravitational acceleration required to achieve certain flybys were based on assumptions that did not match the actual observed motion of the comet. When you use the real data, the need for any non-gravitational forces essentially disappeared. The back and forth between Loeb and his critics highlights a fundamental tension in how science deals with extraordinary claims. On one hand, science should be open-minded, willing to consider unconventional hypotheses, especially when dealing with phenomena we have limited experience with. Interstellar objects are rare, and we have only studied 3 of them. Our sample size is tiny, our understanding is incomplete, and it would be presumptuous to claim we know all the natural processes that could produce unusual properties. In that light, exploring the possibility that some interstellar objects might be artificial is not inherently unreasonable. On the other hand, science also requires rigor, a commitment to using the best available data, and a recognition that extraordinary claims require extraordinary evidence. The problem with Loeb's approach, his critics argue, is not that he is willing to consider the artificial hypothesis, but that he promotes it publicly before the evidence is sufficient to warrant serious consideration, using outdated or cherry-picked data to support his case, and framing the question in ways that make it seem more likely than the evidence actually suggests. This, they worry, confuses the public, undermines confidence in scientific process, and makes it harder to have serious conversations about how we would actually recognize genuine evidence of extraterrestrial technology if we encountered it. The debate over Loeb's methods and conclusions will likely continue for years. But regardless of where you stand on his specific claims about Three-Eye Atlas, the controversy has served a useful purpose. It has forced the scientific community to think explicitly about criteria for identifying artificial objects, about what kinds of observations and measurements would be needed to distinguish technology from nature, about how much evidence would be sufficient to justify such a conclusion. These are conversations worth having, because at some point, if we continue to discover and study interstellar objects, we may encounter something that truly does not fit natural explanations. When that happens, having a framework for how to approach the question rigorously will be essential. But speculation about alien technology aside, Three-Eye Atlas has given us more than enough to think about based purely on its observed properties. The carbon dioxide dominance, the early activity at large distances, the nickel without iron, the unprecedented polarization signature, the green color despite carbon depletion. Each of these represents a puzzle that scientists are still working to understand. And all of these observations are about to be tested in the most extreme way possible, because Three-Eye Atlas is approaching perihelion. Perihelion is the moment of truth for any comet, the point of closest approach to the Sun where temperatures soar, where ices sublimate violently, where structural integrity is tested by thermal stress and tidal forces. For Three-Eye Atlas, perihelion occurs on October 30th, 2025, when the comet will be approximately 1.36 astronomical units from the Sun, just inside the orbit of Mars. At that distance, surface temperatures will reach their maximum. Solar radiation will pour gigawatts of energy onto the nucleus, and sublimation rates will peak. It is the moment when comets reveal their true nature, when fragile structures break apart, when dormant ices suddenly awaken, when everything that has been building during the long approach comes to a climax. What will happen to Three-Eye Atlas at perihelion? There are several possibilities. The most straightforward is that the comet will behave exactly as a comet should. Activity will increase dramatically, the coma will expand, a long tail will develop streaming behind the nucleus as dust and gas are pushed away by solar radiation and the solar wind. The comet will brighten significantly, possibly becoming visible to the naked eye if it were not positioned so close to the Sun in the sky. Sublimation will excavate fresh layers of ice, potentially exposing materials that have been buried since the object formed billions of years ago. And then, as the comet moves away from the Sun and begins its journey back toward the outer solar system, activity will gradually decline, the coma will fade, and Three-Eye Atlas will return to the cold dormancy it knew for the vast majority of its existence. But there are other possibilities. Comets are fragile objects, and the stresses of perihelion can tear them apart. We have seen this happen numerous times. Comet Shoemaker Levy 9 broke into more than 20 pieces before colliding with Jupiter in 1994. Comet Linear disintegrated as it approached the Sun in 2000, fragmenting into dozens of pieces that quickly dispersed. More recently, Comet Atlas, a different object than Three-Eye Atlas despite the similar name, broke apart in 2020, its nucleus splitting into multiple fragments that each developed their own comas. If Three-Eye Atlas fragments at perihelion, we will see a sudden brightening as fresh ice is exposed on the fractured surfaces, followed by the development of multiple condensations in the coma as the fragments separate. This would be scientifically valuable because it would expose the interior composition of the nucleus, material that has been shielded from space weathering and solar radiation. But it would also mean the end of Three-Eye Atlas as a coherent object. The fragments would gradually disperse, their individual masses too small to hold together gravitationally, and eventually they would sublimate away entirely, dissipating into gas and dust that would become part of the interplanetary medium. There is also a possibility that 3I Atlas will undergo a major outburst at perihelion, a sudden, dramatic increase in activity beyond what the temperature increase alone would predict. This can happen if a large pocket of highly volatile material is suddenly exposed, or if pressure builds up beneath an insulating surface layer until that layer ruptures explosively. Outbursts can increase a comet's brightness by factors of 100 or even 1,000, creating spectacular displays that are visible even in daylight. They are unpredictable and short-lived, sometimes lasting only hours or days before activity returns to previous levels. And then there is the scenario that keeps some people awake at night, the possibility that perihelion will reveal something about 3I Atlas that forces us to reconsider our assumptions about what it is. If the object is artificial, if it contains technology, perihelion would be the logical time for that technology to become active. Solar energy is at its maximum. Any systems that require power to operate would have access to more energy than at any other point in the object's journey through our solar system. If 3I Atlas is a probe designed to gather data about our planetary system, perihelion would provide the closest approach to the Sun and the best vantage point for observations. This is speculation, and most scientists would argue it is unnecessary speculation given that natural explanations remain available for all of the comet's observed properties. But the speculation persists because the timing is so convenient. Perihelion occurs when the comet is on the far side of the Sun from Earth's perspective, hidden behind 150 million kilometers of incandescent plasma. We cannot observe it directly during those crucial days when it is closest to the Sun, when activity is at its peak, when anything unusual will be most likely to occur. Ground-based telescopes cannot point anywhere near the Sun without risking damage to sensitive detectors. Space-based telescopes like Hubble and Webb have strict solar avoidance zones to protect their instruments. For a period of roughly 3 weeks, from mid-October through early November, 3I Atlas is effectively invisible to our primary observational assets. There are a few spacecraft that can observe during this period. The Solar and Heliospheric Observatory, SOHO, which monitors the Sun from a position 1.5 million kilometers from Earth in the direction of the Sun, has coronagraph instruments that block out the Sun's disk and can detect objects passing near the Sun. SOHO has discovered thousands of comets over its decades of operation, most of them small sun grazers that plunge so close to the Sun they are vaporized. SOHO will be able to detect 3I Atlas during perihelion passage, but its instruments are designed for solar physics, not for detailed cometry, and its resolution will not be sufficient to reveal fine structure. The Parker Solar Probe, NASA's mission to study the solar corona from closer than any spacecraft has gone before, might also catch glimpses of 3I Atlas, depending on the exact geometry. Parker's wide-field imager can capture objects in the inner solar system, but Parker follows its own highly elliptical orbit with a perihelion inside the orbit of Mercury, and whether it is positioned to observe 3I Atlas at the right time depends on timing that may not align perfectly. The best post-perihelion observations will come from ESA's Jupiter Icy Moons Explorer, or JUICE, a spacecraft currently on its way to Jupiter, but positioned such that it will have an excellent view of 3I Atlas in late November, a few weeks after perihelion. JUICE carries cameras and spectrometers designed to study icy moons, and those same instruments are well suited to observing a comet. The spacecraft will capture images and spectra of 3I Atlas when it is still highly active, when the tail is fully developed, when we can see the aftermath of perihelion and assess how the comet has changed. But all of that is after the fact. The perihelion passage itself, the moment of maximum heating and maximum stress, will occur largely unseen, known to us only indirectly through whatever changes are revealed when the comet emerges from solar conjunction in early December. And that is when the final act of this story will begin. When 3I Atlas reappears in the morning sky, visible again to telescopes around the world, ready to show us whether it survived perihelion intact, whether it fragmented, whether it underwent outbursts, whether anything unexpected happened during those hidden weeks when we could not watch. As 3I Atlas moved through late September and into October, approaching ever closer to the Sun and to its disappearance from view, observations continued from every available facility. The comet was brightening as predicted, developing a more prominent tail, showing increasing activity in all wavelengths. Spectroscopic observations detected additional molecules appearing in the coma as different ices reached their sublimation temperatures. The CN emission continued to strengthen, and now there were hints of other species appearing. Hydroxyl radicals from water sublimation, ionized molecules accelerated by the solar wind, complex organic fragments released from the heating nucleus. Amateur astronomers captured beautiful images showing the comet's green coma and the developing dust tail. The tail was still relatively short compared to the great comets that developed tails stretching for millions of kilometers, but it was visible, a clear streamer of material being pushed away from the nucleus by radiation pressure. The ion tail, composed of ionized gas, accelerated to high speeds by the solar magnetic field, was harder to see but appeared in some long exposure images as a fainter, straighter structure compared to the broad, curved dust tail. And then, in mid-October, 3I Atlas moved too close to the Sun for safe observation. Telescopes were commanded to avoid the region of sky where the comet now resided, and the flow of data stopped. The international collaboration that had been observing and analyzing this object for more than 3 months was forced to pause, to wait to hope that when the comet re-emerged, it would still be intact. During that waiting period, scientists worked on analyzing the data that had already been collected. Papers were written, models were refined, debates continued about what the various observations meant and how they should be interpreted. The tally of published research papers specifically mentioning 3I Atlas climbed past 70, a remarkable number for an object discovered so recently. Each paper added a piece to the puzzle, a measurement, a constraint, a theoretical interpretation, a comparison with other objects. The picture that emerged was of a comet, unlike any we had studied before, a visitor from an environment radically different from our own solar system, carrying in its composition and behavior clues about the diversity of planetary systems throughout our galaxy. But even as scientists worked to understand the comet through the lens of conventional astrophysics and cometry, the public conversation had taken on a different character. On social media, on blogs, in forums and comment sections, people were speculating about what 3I Atlas really was. Some dismissed it as just another comet, interesting to scientists but not particularly relevant to everyday life. Others saw in it a profound mystery, an object whose anomalies could not be easily explained and whose true nature remained hidden behind walls of scientific jargon and institutional silence. Conspiracy theories began to circulate, ideas that governments knew more than they were saying, that the true nature of 3I Atlas was being concealed for national security reasons or to prevent panic. Some pointed to the fact that Mars orbiters from NASA, ESA, China, and the UAE had all observed 3I Atlas during its close approach to Mars on October 3rd, but none had released detailed images from those observations. The Perseverance rover had captured faint streaks in its navigation cameras that amateur analysts claimed showed the comet, but the high-resolution images from the Mars Reconnaissance Orbiter's high-rise camera, capable of resolving features 30 kilometers across at the comet's distance, had not been publicly released. NASA attributed the lack of immediate data release to the government shutdown that had furloughed thousands of employees starting October 1st, just 2 days before the Mars flyby. Without staff to process images and prepare data for public release, the agency said, there would inevitably be delays. ESA, operating under different administrative structures, simply noted that data was being analyzed and results would be published when ready. China and the UAE offered no public explanation for the absence of images from their missions. This silence, whether deliberate or simply the result of bureaucratic and technical delays, fueled speculation that something unusual had been observed, something that required careful review before being shared with the public. The speculation was probably unfounded, the result of people seeing patterns where none existed, ascribing significance to delays that had mundane explanations. But it illustrated how a controversial discovery, or even just an unusual one, can take on a life of its own in the public imagination, becoming a screen onto which people project their hopes, fears, and preconceptions about the universe and our place in it. For those of us who have followed this story from the beginning, who have read the scientific papers and followed the observational campaigns, the truth is both simpler and more profound than the conspiracies suggest. 3I Atlas is almost certainly a natural object, a comet formed billions of years ago around a star we will never identify, shaped by processes we are still working to understand, carrying in its ice and dust a record of conditions that existed in its birthplace when the object first condensed from the protoplanetary disk. It is almost certainly not a spacecraft, not a probe, not a deliberate messenger from an alien civilization, but almost certainly is not the same as certainly. Science deals in probabilities and evidence, not absolute truths, and the evidence, while strongly favoring natural origin, has not entirely closed the door on other possibilities. The nickel anomaly remains unexplained. The polarization signature remains unprecedented. The trajectory alignments, while not impossible by chance, are statistically unusual. Each of these could have natural explanations that we simply have not thought of yet. Processes that occur in interstellar comets but not in solar system comets. Chemistry that operates under conditions we have not encountered before. What we need is more data. More observations, higher resolution, different wavelengths, new techniques. We need to track 3I Atlas as it moves away from the Sun, measuring how its activity declines, how its composition changes, how its orbit evolves under the subtle influences of non-gravitational forces from outgassing. We need to compare it with future interstellar visitors, building up a larger sample size so we can determine what is typical and what is truly anomalous. We need theoretical work to model the conditions in other planetary systems and predict what kinds of compositions and structures we should expect. And yes, we need to keep an open mind to the possibility that one day, perhaps with 3I Atlas or perhaps with some future visitor, we will encounter something that cannot be explained naturally. Something that forces us to confront the reality that we are not alone. That possibility, however remote, is part of what makes the study of interstellar objects so compelling. These are not just rocks. They are ambassadors from distant reaches of the galaxy, carriers of information about environments we cannot directly observe, potential messengers from civilizations we have never met. Every interstellar object that enters our solar system is an opportunity, a chance to learn something fundamentally new about the cosmos, a window into the diversity and complexity of the universe beyond our immediate neighborhood. 3I Atlas has given us that opportunity. In the months since its discovery, it has challenged our assumptions, forced us to refine our models, revealed new phenomena that we need to understand. It has shown us that interstellar space is not uniform, that comets from other star systems can have compositions radically different from those we are familiar with, that the processes of planet formation and evolution produce a wider range of outcomes than we had appreciated. These are valuable scientific lessons, advances in our understanding that will inform how we think about planetary systems for years to come. And the story is not over. In just a few weeks, 3I Atlas will emerge from behind the Sun, visible once again to telescopes on Earth and in space. It will be different than when it disappeared. Perihelion will have changed it, sculpted its surface, driven off layers of ice, perhaps cracked its structure, perhaps released materials that have been locked away since it formed. Observatories around the world are preparing for that moment, scheduling observation time, coordinating campaigns, readying instruments to capture the first images of the post-perihelion comet. Amateur astronomers are checking their equipment, planning their imaging sessions, eager to see what 3I Atlas looks like after its fiery passage near the Sun. And scientists are developing observation plans, lists of measurements to make, spectra to capture, comparisons to perform between the pre-perihelion and post-perihelion states. The anticipation is palpable across the astronomical community. Every perihelion passage is an experiment, a test of our understanding, an opportunity to see theory confronted by reality. But this perihelion is special because the object being tested is unlike anything we have studied before. Will 3I Atlas conform to our predictions, or will it surprise us yet again? Will the carbon dioxide sublimation follow the expected curves, or will new volatiles emerge from the heated interior? Will the nickel emission continue, perhaps joined by other metals, or will it fade away as surface materials are stripped off? Will the nucleus remain intact, or will we discover that it has fragmented into pieces that are now separating along slightly different orbits? These questions will begin to be answered in early December when the first telescopes regain visual contact with the comet. But the full story will take months to unfold as observations continue and data is analyzed. The beauty of astronomical investigation is that it unfolds at this measured pace, allowing time for careful thought, for debate, for the gradual construction of understanding through the accumulation of evidence. There is no rush, no deadline beyond perihelion itself. The comet will be observable for many more months as it moves outward from the Sun, gradually fading as it returns to the cold depths of space, but still visible to large telescopes, still releasing information about its nature with every photon of light it reflects or emits. In the meantime, as we wait for 3I Atlas to re-emerge, it is worth reflecting on what this object has already taught us and what it represents for the future of interstellar object studies. Before Oumuamua arrived in 2017, interstellar objects were entirely theoretical. We knew they must exist. Simple logic and orbital dynamics told us that planetary systems must occasionally eject comets and asteroids into interstellar space, and that over billions of years the galaxy should have accumulated a substantial population of these wanderers. But we had never detected one. The arrival of Oumuamua changed that, proving that interstellar objects do indeed visit our solar system and can be detected with modern surveys if we are looking carefully enough. Oumuamua was followed 2 years later by 2I Borisov, confirming that interstellar visitors are not once-in-a-lifetime events, but occur with some regularity. And now, just 6 years after the first detection, we have 3I Atlas, the third confirmed interstellar object, and the most thoroughly studied one yet. This rapid succession of discoveries tells us that we are entering a new era of astronomy, an era where interstellar objects are routine targets of observation, where we can begin to build up statistics, where comparison between different objects allows us to identify patterns and anomalies. The impact of this new era extends far beyond the study of comets. Interstellar objects are time capsules, frozen records of the conditions that existed in their parent planetary systems billions of years ago. By studying their compositions, we learn about the chemistry of star-forming regions, about the processes that create planets and smaller bodies, about the diversity of environments that exist around other stars. This information feeds directly into our understanding of how planetary systems form and evolve, how common Earth-like planets might be, how frequently the conditions necessary for life might arise elsewhere in the galaxy. Interstellar objects also provide a way to study environments that are otherwise completely inaccessible to us. The nearest star system beyond our Sun, Proxima Centauri, is 4.2 light-years away. Even traveling at the speed of our fastest spacecraft, it would take tens of thousands of years to reach it. We can observe distant stars through telescopes, measure their properties, detect planets orbiting them. But we cannot collect samples, cannot perform detailed chemical analysis, cannot touch and examine the materials that make up those distant worlds. Interstellar objects change that equation. They bring samples from other star systems to us, delivering materials that formed in alien environments, carrying information encoded in their compositions and structures that we can extract and study in detail. This is why the discovery of 3I Atlas matters, why scientists are devoting substantial telescope time to observing it, why theoretical papers are being written to explain its properties. It is not just another comet. It is a visitor from a distant corner of our galaxy, a messenger carrying news from a place we will never visit, a scientific treasure that has fallen into our laps and will teach us things we could learn no other way. But the significance of 3I Atlas extends beyond science. There is something profound about the very existence of these objects, something that speaks to the interconnectedness of the cosmos, to the fact that despite the vast distances between stars, the galaxy is not entirely fragmented into isolated islands. Material flows between star systems, slowly but continuously, mixing and redistributing over cosmic timescales. Every star, every planet, every comet has some probability of eventually being ejected into interstellar space and wandering for millions or billions of years before perhaps encountering another stellar system. The galaxy has a circulation system, a slow metabolism that moves matter from system to system over eons. This means that the materials in our own solar system, the rocks and ices that make up Earth and the other planets, the carbon and nitrogen and oxygen that make up our bodies, have their own deep history that predates the formation of the sun. Some fraction of the atoms in your body right now were once part of interstellar objects that wandered through other star systems before the sun existed, that witnessed the birth and death of stars, that traveled across hundreds of light years of empty space before eventually being swept up into the cloud of gas and dust that collapsed to form our sun and its planets. You are made of star stuff, as Carl Sagan famously said, but more than that, you are made of wanderer stuff, atoms that have journeyed across the galaxy, that have seen things you cannot imagine, that carry in their very structure the history of cosmic evolution. And when you look up at 3I Atlas, when you see this faint smudge of light against the stars, you are looking at an object that is still on that journey, still wandering, temporarily passing through our neighborhood before continuing on into the endless dark between stars. There is poetry in this, a kind of cosmic kinship. We are not isolated from the rest of the universe. We are part of a vast exchange system, connected to distant stars, not just by light and gravity, but by the physical flow of matter. The same processes that ejected 3I Atlas from its birth system operate in our own solar system, gradually scattering comets into the Oort cloud and beyond, some of which will eventually escape entirely and become interstellar travelers themselves, carrying with them samples of Earth's solar system, perhaps even organic molecules or microbial life delivered to other stars millions of years in the future. This idea, called panspermia, has been discussed for over a century. Could life itself spread between star systems, transported on comets and asteroids? The answer depends on many factors, on whether microorganisms can survive the radiation and cold of interstellar space for millions of years, on whether they can remain viable through the violent process of impact when an interstellar object collides with a planet, on whether the receiving planet has conditions suitable for the organisms to take hold and multiply. Most scientists are skeptical that panspermia operates efficiently enough to be a major factor in the origin of life. But it cannot be entirely ruled out, and the discovery of interstellar objects like 3I Atlas makes the hypothesis testable in principle. Imagine if we could rendezvous with 3I Atlas, send a spacecraft to intercept it, land on its surface, drill into the nucleus, extract samples of the ice and dust. What would we find? Ancient water molecules frozen for 4 billion years, unchanged since the comet formed. Organic compounds, amino acids perhaps, the building blocks of proteins synthesized in the cold chemistry of the interstellar medium or in the primordial disk around a young star. And could those samples contain something else? Something unexpected? Preserved microorganisms from another world? Dormant spores waiting for the right conditions to awaken? Molecular fossils of life that evolved under an alien sun? This is still science fiction, but it is science fiction that is gradually becoming less fictional. We already have the technology to send spacecraft to intercept comets. The European Space Agency's Rosetta mission successfully orbited and landed on a comet in our own solar system, spending 2 years studying it up close, deploying a lander to touch the surface, analyzing gases and dust, mapping the nucleus in extraordinary detail. If we can do that for a solar system comet, there is no fundamental reason we could not do it for an interstellar one, given enough warning, enough preparation time, and sufficient resources. The challenge with interstellar objects is that they move fast and they do not stay long. Oumuamua was only discovered on its way out of the solar system, too late to launch an intercept mission. By the time we realized what it was already moving away from the sun faster than any spacecraft we could build. Borisov gave us more warning, discovered while it was still inbound, but even so, there was not enough time to design, build, and launch a mission before it passed through and left. 3I Atlas, discovered 5 months before perihelion, would provide just barely enough time for an emergency mission if one had been prepared in advance. But no such mission exists. Building a spacecraft capable of intercepting an interstellar object requires years of planning, construction, and testing. The launch window is narrow, the trajectory is complex, the technical challenges are substantial. It is not something that can be improvised. But the astronomical community has learned from these missed opportunities. Plans are now being developed for a rapid response mission, a spacecraft kept on standby that could be quickly adapted and launched on short notice when the next interstellar visitor is discovered. Such a mission would not be cheap. It would require maintaining expensive hardware and launch capabilities in a state of readiness potentially for years before an appropriate target appears. But the scientific payoff would be immense. The first up-close study of an object from another star system. The first samples returned from beyond our sun's influence. Possibly the first detection of extraterrestrial organic chemistry or even biology. The discovery of 3I Atlas has lent urgency to these plans. Here is an object that exhibits multiple anomalies, that has sparked intense scientific interest and public fascination, and we are limited to observing it from millions of kilometers away with telescopes. Imagine what we could learn if we could send instruments to measure its properties directly. If we could land on its surface and watch as ices sublimate and gases vent into space. If we could collect samples and return them to laboratories on Earth for analysis with instruments far more sensitive and sophisticated than anything that can fit on a spacecraft. These ambitions will likely have to wait for the 4th or 5th or 10th interstellar visitor. But they will happen. The technology exists, the scientific justification is clear, and the human drive to explore, to touch, to physically investigate the unknown is too strong to be denied forever. Within your lifetime, if you are young, or perhaps within the lifetime of your children if you are older, a spacecraft will intercept an interstellar object, and humanity will hold in its hands a piece of another star system. Until then, we study these visitors from afar, learning what we can from the light they reflect and emit, building our understanding piece by piece, observation by observation. developing the theoretical framework that will guide future missions and future interpretations. And we wait for the next discovery, knowing that somewhere out there, another interstellar object is already on its way toward us, moving through the dark between stars, carrying its own secrets, ready to surprise us with new anomalies and new questions. As you drift towards sleep tonight, imagine that journey. Imagine a chunk of ice and rock, perhaps no larger than a mountain, perhaps much smaller, ejected from a planetary system hundreds of light years away, millions or billions of years ago. Imagine it tumbling through the void, passing through vast clouds of interstellar gas and dust, navigating the gravitational fields of passing stars, slowly making its way across distances so large that light itself takes centuries to traverse them. For most of its existence, this object is utterly alone, surrounded by emptiness, lit only by the faint glow of distant stars. There is no sound in space, no air to carry vibrations. There is only silence, profound and absolute, broken perhaps occasionally by the faint ticking of cosmic rays striking the surface. Individual particles moving at nearly the speed of light, depositing tiny amounts of energy, gradually darkening and chemically altering the outer layers of ice. The object's rotation might gradually slow over millions of years as internal friction dissipates angular momentum. Its orbit through the galaxy curves gently under the influence of the Milky Way's gravitational potential, the combined mass of hundreds of billions of stars pulling it this way and that, changing its trajectory by imperceptible amounts, but over such vast stretches of time that these tiny changes accumulate into completely different paths. And then, after traveling for eons, after passing near countless stars without ever quite encountering one closely enough to interact, after wandering through perhaps thousands of light years of space, the object detects something new. Not consciously, of course. It has no awareness, no sensors, no ability to perceive, but the laws of physics perceive on its behalf. Gravity perceives, light perceives. And what they perceive is a star ahead, a yellow dwarf star, very much like billions of others in the galaxy, but this one lies directly in the object's path. The encounter unfolds over years, then months, then weeks. At first, the star is just one point of light among countless others, but gradually, slowly, it brightens. The object begins to feel its gravity, a gentle tug that curves the trajectory slightly, pulling the object inward toward the inner regions of a planetary system it has never visited, toward worlds orbiting this star, toward fates unknown. As it falls inward, the star's light intensifies. For billions of years, this object has been frozen solid, every molecule locked in place, time itself seemingly suspended in the absolute cold of deep space. But now, warmth begins to arrive, photons carrying energy from the approaching star, striking the surface, depositing heat, raising the temperature by fractions of a degree, then by whole degrees, then tens of degrees. And at some threshold, the ice begins to change. Molecules that have been motionless for cosmic ages begin to vibrate. Bonds begin to weaken. The most volatile ices, those with the lowest sublimation temperatures, begin to transition directly from solid to gas without passing through a liquid phase. The object begins to outgas, releasing molecules into the near vacuum of space, creating a tenuous atmosphere that grows and spreads as more ice sublimes. This is the moment of awakening, when a dormant comet becomes active, when it transforms from a dark, frozen body into something dynamic, something that glows, something that leaves a visible trace across the sky. And this is the moment when creatures living on one of the planets orbiting this star, creatures who have developed technology to detect faint objects in their sky, notice something unusual, something moving along a trajectory that does not match any known object in their system. They point their telescopes at it. They measure its motion, calculate its orbit, realize with growing excitement that this object has come from outside, from the space between stars, from somewhere impossibly far away. They observe it intensely as it approaches, measuring everything they can, trying to understand what it is, where it came from, what it is made of. They debate its properties, argue about its anomalies, wonder whether it might be something more than just a natural comet. And the object, unaware of this attention, continues on its path, swinging around the star, passing through perihelion, feeling the maximum heat and stress, perhaps fracturing under the strain, perhaps releasing materials that have been locked away since its formation, perhaps surviving intact to continue its journey back out into the dark. This is the story of 3 Atlas. This is the story of every interstellar object. They are travelers, wanderers, ambassadors from the vast spaces between stars, and for a brief moment, they pass through our neighborhood, allowing us to study them, to learn from them, to marvel at the fact that we share this galaxy with countless other star systems, each producing its own cast-off materials, each contributing to the slow mixing and recycling of matter across cosmic scales. The universe is not static. It is dynamic, flowing, constantly in motion. Stars are born and die. Planets form and are destroyed. Comets are ejected and captured. And through it all, matter circulates. Atoms that were forged in the cores of ancient stars being redistributed across the galaxy, becoming part of new stars, new planets, new comets, eventually perhaps becoming part of living organisms achieving consciousness, looking up at the sky and wondering about their origins. You are part of that story. Every atom in your body has its own history, its own journey through space and time. The calcium in your bones was created in supernova explosions billions of years ago. The iron in your blood was forged in the heart of dying stars. The carbon in your DNA may have spent millions of years drifting through interstellar space before eventually being incorporated into the cloud that formed our sun. And someday, in the incomprehensibly distant future, when the sun has exhausted its fuel and swelled into a red giant, when the Earth has been consumed or rendered uninhabitable, the atoms that once made up your body will be released back into space. Some will be drawn into the sun as it collapses into a white dwarf. Others will be blown outward by stellar winds, joining the interstellar medium, perhaps eventually condensing into new comets, new planets, orbiting new stars, participating in new chapters of the cosmic story. This is the perspective that interstellar objects like 3I Atlas offer us. They remind us that we are not isolated, not separate from the rest of the universe, but deeply integrated into its flows and cycles. They connect us to other star systems, to other times, to the deep history of the galaxy. They humble us with their ancient origins and their vast journeys, and they inspire us to look outward, to wonder what else might be out there, to imagine the possibility that someday, somehow, we might send our own ambassadors into the space between stars, carrying messages, carrying knowledge, carrying the evidence that here, around this one ordinary yellow star, life emerged, developed intelligence, looked up at the cosmos and tried to understand. As 3I Atlas moves through its closest approach to the sun, hidden behind the glare, inaccessible to our telescopes, it undergoes its transformation alone, unwatched. Gases stream off its nucleus at hundreds of meters per second, carrying dust particles that catch the sunlight and begin to form a tail stretching behind the comet. The nucleus itself is being sculpted by the heating. Smooth areas becoming rough as ices sublimate unevenly, fractures opening as temperature gradients create internal stresses. Perhaps entire sections breaking away to form smaller fragments that will follow their own slightly different orbits. We cannot see this happening in real time. We will only see the results when the comet emerges from behind the sun in early December, when we can compare its post-perihelion appearance to the pre-perihelion observations and infer what must have occurred during those hidden weeks. This is how astronomy often works, piecing together narratives from incomplete data, inferring processes from their outcomes, building models that explain what we observe, even when we cannot directly witness the events themselves. But the fact that we cannot watch perihelion directly does not diminish its significance. The transformation is happening regardless of our ability to observe it. The comet is following the laws of physics, responding to the environment it finds itself in, changing in ways that are determined by its composition and structure and history. Reality continues independent of observation, a reminder that the universe does not exist for our benefit, does not arrange itself for our convenience, simply is following its own logic, creating its own patterns, whether or not anyone is paying attention. There is something deeply meditative about this realization, something that can help quiet the constant chatter of the mind and ease the transition into sleep. The universe is vast beyond comprehension. Events are occurring constantly, stars exploding, planets forming, comets venting gas, galaxies colliding, black holes consuming matter, cosmic rays traversing the void at relativistic speeds. All of this happens without your participation, without your awareness, without any need for your attention or concern. You can let go of the need to understand everything, to control everything, to be aware of everything. The cosmos will continue without you. 3i Atlas will complete its journey whether you think about it or not. The stars will shine, gravity will operate, time will flow forward. You can rest in the knowledge that the universe is managing itself quite well, that the laws of physics are reliable, that everything is unfolding exactly as it must. This perspective is not nihilistic. It does not diminish the importance of your life or your actions, but it provides context, a sense of scale that can help put daily worries and anxieties into proper perspective. The argument you had today, the deadline you are stressed about, the relationship challenge you are facing, these are real and important to you. But set against the backdrop of cosmic time and cosmic space, they are temporary, local, small. They will pass. Everything passes, and that is okay. That is how things are meant to be. Impermanence is built into the structure of reality. Stars do not shine forever. Planets do not remain in their orbits for eternity. Even the atoms themselves will eventually decay given enough time, everything in the universe slowly running down, entropy increasing, complexity gradually giving way to simplicity. But impermanence is not something to fear. It is what makes change possible, what allows new forms to emerge, what enables the universe to be creative and dynamic, rather than static and dead. 3i Atlas itself embodies impermanence. It formed billions of years ago and will not exist billions of years from now. Eventually, all its ices will sublime away, all its dust will disperse, and nothing will remain but the atoms that once composed it, scattered across light years, perhaps incorporated into new structures, new objects, participating in new stories. The comet's current existence as a coherent body is temporary, a brief episode in the eternal recycling of matter and energy. And yet, for this moment, it exists, it is real. It occupies a specific location in space and time. It can be observed, studied, wondered about. Its existence matters not because it will last forever, but precisely because it is temporary, because this particular configuration of atoms has never existed before and will never exist again. Because this journey through our solar system is unique, unrepeatable, precious in its specificity. The same is true for you. Your existence is temporary. The specific arrangement of atoms that makes up your body and brain right now will not persist. You are constantly changing, cells dying and being replaced, thoughts arising and passing away, experiences accumulating and then fading into memory. You are not a static thing, but a process, a pattern of activity maintained for a time before eventually dissolving back into the matter and energy from which you emerged. This might sound depressing, but it need not be. The temporary nature of existence is what makes each moment valuable. If you lived forever, if nothing ever changed, if every moment were the same as every other moment, would any particular moment matter? It is precisely because time is limited, because experiences do not last, because people and places and moments are unique and unrepeatable, that they have meaning and significance. So as you prepare for sleep, as your consciousness begins to dim and your thoughts start to dissolve, you can rest easy in the knowledge that this is natural. This is how things are supposed to be. Just as Three-Eye Atlas will eventually fade from view as it moves back out into interstellar space, just as its activity will decline as it moves farther from the sun's warmth, just as it will eventually return to the cold dormancy it has known for most of its existence, you too are allowed to let go, to fade into unconsciousness, to rest. Sleep is a small version of the larger cycles of existence. You dissolve into it each night and re-emerge each morning, slightly different, slightly changed, but continuous enough that you recognize yourself as the same person. Dreams arise during sleep, strange and vivid and meaningful in ways you cannot always articulate, and then they fade, usually forgotten within minutes of waking, but occasionally leaving traces, impressions, feelings that linger into your waking life. The universe dreams too, in a sense. Stars dream in nuclear fire, fusing hydrogen into helium, releasing energy that radiates outward for millions of years before escaping into space. Galaxies dream in gravity, their spiral arms slowly rotating over hundreds of millions of years, new stars forming in dense clouds, old stars dying in spectacular explosions. And comets like Three-Eye Atlas dream in ice, frozen stories waiting to be told, preserved messages from ancient times, gradually releasing their secrets as they warm, as they sublimate, as they journey through the inner regions of planetary systems. Your dreams tonight might include images of space, of comets, of vast distances and deep time. Or they might be about something completely different, the random firing of neurons as your brain processes the day's experiences and consolidates memories. Either way, they are part of the natural process of consciousness, the mind organizing itself, making sense of information, preparing for tomorrow. And when you wake, Three Atlas will still be there, continuing its journey, moving day by day toward its re-emergence, carrying its mysteries with it, waiting to reveal what perihelion has done to it. Whether it has survived intact or fragmented into pieces, whether it has new surprises in store, or will conform more closely to expectations now that the most volatile ices have been stripped away. The scientific community waits with patient anticipation. Telescope time has been scheduled for December and January and beyond. Instruments stand ready. Plans have been made, and when the first images come back, when spectroscopy reveals the post-perihelion composition, when we can measure whether the orbit has changed due to outgassing forces, when we can assess the comet's brightness and activity level, the next phase of investigation will begin. Papers will be written comparing pre- and post-perihelion observations. Models will be refined based on what actually happened versus what was predicted. Debates will continue about the unusual properties, perhaps with new data that resolve some questions while raising others. And gradually, slowly, over months and years, a consensus will emerge about what Three-Eye Atlas is, where it came from, what it tells us about conditions in other planetary systems. But that is work for tomorrow, for next week, for next year. Tonight, there is only the quiet darkness, the gentle rhythm of breath, the gradual relaxation of body and mind, the surrender to sleep. The comet is where it is, doing what it does, following its trajectory through space and time. The universe is unfolding according to its own logic, creating and destroying, combining and separating, forever in motion, yet somehow deeply still at its core. You are a part of that universe, made from the same materials, following the same laws, participating in the same great cycles of existence. And in this moment, your participation consists simply of being, of breathing, of allowing consciousness to dim and rest to come. Let your thoughts about 3i Atlas drift away now. Let the questions fade. Let the wonder and curiosity and fascination settle into a peaceful awareness that the cosmos is vast and mysterious and beautiful, and that you have had the privilege of learning about one tiny piece of it, one visitor from the depths of space, one story among countless stories that are unfolding everywhere, all the time, in the endless expanse of the universe. The comet will continue its journey without your conscious attention. The scientists will continue their work. The data will be collected and analyzed, and you can rest knowing that the universe does not require your constant vigilance, that it is perfectly capable of managing itself, that you are allowed to let go, to sleep, to dream, to wake refreshed tomorrow, ready to engage with the world again, but for now simply allowed to rest. As sleep approaches, imagine yourself floating in the darkness of space, far from Earth, far from the sun, in the deep silence between stars. There is no up or down, no reference point, nothing but the distant glow of the Milky Way surrounding you, millions of stars creating a faint luminescence that barely penetrates the darkness. You are weightless, drifting, at peace, and far away, so far that you cannot see it directly. Only imagine it. 3i Atlas continues its eternal journey, a tiny fragment of ice and rock and mystery, carrying the history of another star system, another time, another place. For a brief moment, your consciousness and this comet have intersected, have shared the same moment in time, have been connected by your awareness and curiosity. And now that intersection is fading as you drift towards sleep, as the comet moves along its path and you move along yours. Both of you part of the same vast cosmic dance, both of you precious in your uniqueness, both of you temporary manifestations of the universe's endless creativity and change. Rest now, sleep deeply. The comet knows the way. The stars will guide it, and you safely here on Earth, surrounded by the familiar comfort of your bed. Your home, your life, can let everything else fade away, can surrender to the gentle darkness, can trust that tomorrow will come, that the story will continue, that the universe will still be here when you wake, still vast, still mysterious, still filled with wonders waiting to be discovered. The journey of 3i Atlas through our solar system is just one story among infinite stories, and your journey through this night, from waking consciousness into the depths of sleep and back again to tomorrow's dawn, is another story, equally valid, equally important, equally precious. Both journeys continue now without words, without thought, simply unfolding as they must, following the natural patterns of existence, participating in the eternal dance of matter and energy and consciousness and time. Sleep well. Dream gently. The cosmos watches over you, not consciously, not deliberately, but through the simple fact of its existence, its vastness, its beauty, its reliable and predictable operation, according to laws that have governed it for billions of years and will continue to govern it for billions more. You are safe. You are home. You are part of something infinitely larger than yourself, yet also infinitely intimate, because you are made of it. You are it looking at itself, wondering about itself, eventually returning to itself in sleep and in death, and in the endless recycling of matter and energy that characterizes all existence. Rest now in that knowledge. Let it comfort you. Let it hold you. Let it carry you gently into sleep, into dreams, into the temporary dissolution of consciousness that is necessary for renewal, for restoration, for the continuation of life. The story of Three-Eye Atlas is also the story of the universe telling itself about itself through the medium of human consciousness and curiosity. And as you drift away now, as sleep claims you, the story continues, always continuing, never ending, because there is no end to the universe. Only transformation, only change, only the eternal present moment extending forward and backward through time, connecting everything to everything else, making all of existence one unified whole of which you are an inseparable part. May your sleep be deep and peaceful. May your dreams be gentle. May you wake refreshed, carrying with you the sense of connection to something vast and ancient and beautiful. May the story of Three-Eye Atlas, this tiny visitor from the depths of space, remind you that you too are a traveler, a wanderer, making your own journey through the cosmos, temporary but real, small but significant, part of the grand unfolding of existence itself. And may you rest now, knowing that everything is exactly as it should be, that the universe is taking care of itself, that you can let go of worry and fear and anxiety and simply breathe, simply exist in this moment, this precious moment, before sleep takes you into its gentle embrace and carries you away to wherever it is that consciousness goes when it releases its grip on waking life. The comet journeys on through the darkness. You journey on through sleep. Both journeys are sacred. Both journeys matter. Both journeys are, in their own way, home. Rest now. Sleep deeply. All is well. The universe continues, and so do you. Good night.